Hi, this is Mrs. Follett, and in this video we'll continue our work with rational exponents and work with some exponent rules to simplify. So our basic steps are going to be convert our radical expressions into exponential expressions. So we need to remember our basic rule that if I have the nth root of x to the m, that would be x to the m divided by n. Then we're going to use laws of exponents to simplify, and then we will convert back to radical notation. So I am assuming that you know all of these rules of exponents. The ones that you might be a little bit less familiar with might be this zero exponent rule. So anything to the power 0 is 1 except 0 to the power 0, and the negative exponent rule, a to the negative n, is 1 over a to the n. But we've gone over previously the power rule, the product rule, the power rule, and the products and quotients rules. So let's go ahead and look at an example and see how this works. So example 1 says simplify and assume all variables represent positive numbers, so we don't have to worry about that pesky absolute value trick. So to start out, we will convert anything that is in radicals into exponent notation. So this would be x to the 15/3. And then we're just going to actually do the math. 15/3 is 5, so this is just x to the 5th. And that is fully simplified. Part B, we are going to do a to the 6th, b to the 6th, to the 1/12th power, using our definition of exponent rules. Then we're going to do the product to a power rule. So when I have a product raised to a power, I raise each thing to that power. Then I'm going to reduce, so I get a to the 1/2, b to the 1/2. Now that's the same thing as a times b, both to the 1/2, so using that product to power rule in reverse, and that just means the square root of ab. So notice we started in radical form, we transitioned to exponents, we did some exponent rules, we did some simplifying, some exponent rules, but then we went back to the radical. Okay, part C, it's got radicals within radicals. So we'll just start from the inside. So from the inside, I have a squared, b squared, which would be raised to the 1/4. And so this whole thing represents that. And then the whole thing would be raised to the 1/3 power. So I'm going to start actually by doing the power to a power right here and make this a squared times b squared to the 1/12th power. Now notice when you take the cube root of a 4th root, it essentially turns into a 12th root. Then similar to the last problem, a to the 2/12 times b to the 2/12, or a to the 1/6 multiplied by b to the 1/6. Those are both to the 1/6 power, so a times b to the 1/6, or the 6th root of ab. Part D is something that we used in the last section when we were taking 4th roots. We showed, or we at least used, that a 4th root was the square root of a square root. And we'll see how that works. So if I have the 4th root of x, that is the same thing as x to the 1/4. If I have the square root of the square root of x, that's the same thing as x to the 1/2 on the inside, to the 1/2, which is the outside square root, which is x to the 1/4. So it turns out that they are the same thing. So the 4th root of x is the same thing as doing the square root of the square root of x. This is a handy trick if you're doing something like the 4th root of 81. You can do the square root of the square root of 81. So the square root of 9, which is 3. Okay, let's do some more exponent rules. And so now we're doing things that are kind of a mixture between exponents and radicals. So we are simplifying, and again, assuming we have positive exponents. So something like this, x to the 3/5 over x to the 1/10. We are going to use the quotient rule, which says if you have two of the same bases, so both x's, divided, you subtract their exponents. And we need a common denominator, so I'm going to say x to the 6/10 subtract 1/10. which is x to the 5/10, or x to the 1/2. Now, because the original expression was in exponent notation, I can go ahead and leave this in exponent notation. So our general rule with this and most other problems is just to match the form of the original expression. So the original expression was in exponent, so we're just going to leave it in exponent notation to match that original form. Okay, let's take a look at part B. So you have 81 to the 1/4 times x to the 2/3 cubed. We can do things kind of in whatever order that we want. I could go ahead and take care of this 4th root of 81, or I could do the product to a power, which would make this 81 to the 3/4, and then this would make this x to the 6/3. 81 to the 3/4 means do the 4th root of 81 and then cube it, and then this would be x squared. Well, the 4th root of 81 we just saw on the previous page is 3, and 3 cubed is 27. So this is 27x squared. Part C says to write as a single radical. And I've got a cube root multiplied with a square root. And it doesn't really seem like we can do anything with that until we recognize that we can rewrite this as x to the 1/3 multiplied by x to the 1/2. Now our exponent rules for same bases when they're multiplied is to add their exponents. So this would be 1/3 plus 1/2. We need a common denominator, so 2/6 plus 3/6, which is x to the 5/6. But since the original expression started in radicals, I need to take this answer back to a radical, which would be the 6th root of x to the 5th, or you could write this as the 5th power of the 6th root of x. This form is usually easier to use when we are evaluating, so if I was plugging an actual value of x in. This form is much simpler to write and doesn't require extra parentheses, and also would be easier to put in Pearson. So I would stick for this form for Pearson and this form for evaluating. Okay, let's do one that has both mixed variables and mixed roots. So same thing. I need to put this 2x in parentheses. So I'm going to do 2x to the 1/5, and then I'm going to do y to the 1/3. Now this isn't like the last problem where I have similar bases, so I can't just add their exponents. So instead what I need to do is try to get them to a common denominator on the exponents, or a common root. So I need to get to a common root. And the common root would be the lowest common denominator, which would be 15. So I'm going to build this one up just by multiplying by a 1 to get them to both be to 15ths. So I have 2x to the 3/15, and I have y to the 5/15. Now they have different numerators, but they have the same denominator. And remember, the denominator is the exponent of the root. So if I wanted, I could write this as the cube of 2x multiplied by y to the 5th, all to the 1/15. Or I could write this as the 15th root of 8x cubed y to the 5th. And I got that 8 by just doing the product to power rule, doing the 2 cubed, which is 8, and then the x cubed. So a little bit different strategy here, just getting that common denominator so that I could get them under the same root as each other. So that should get us started on the section 5.2 notes. There's still more in the notes, and you're not responsible for going any further than this video goes. So make sure that when I come back that you have completed all of the section 5.1 notes and watched the accompanying videos, that you have completed your 5.1 Pearson Realize, and that you have completed the 2 pages of notes that correspond with 5.2.